In this experiment, we will be synthesizing a full adder logic, which is a simple combinational logic returned in Verilog. Note, this procedure is generally applicable to other simple combinational logics such as 4:1 mux, 4-bit priority encoder, and it can even be applied to sequential logics like serial adder, which in general will be returned in FSM model. I will be addressing the serial adder synthesis and place and routing process in the next experiment, which will be a case study experiment. As of now, there are two things to be noted here. This general procedure will differ majorly with respect to your Verilog coding, and you can follow any type of coding style. That is, you can either follow structural, data flow, or even behavioral format to describe your design, but ensure that it adheres to RTL coding standards. And the second thing we have to note is that in the final experiment of serial adder FSM, we will be modifying some attributes in our constraint or the SDC file. Thus, apart from these differences, the entire procedure is common to this experiment and the next coming experiment. Now, we will get into our objective of this experiment. Our objective for this experiment would be to first understand the basics of RTL coding, and then to understand the synthesis process flow by looking into the input outputs of synthesis flow. Followed by this, we will look into the contents of .lib file and the .sdc file. Basically, in this third objective, we will be spending some time in the process of improving our understanding in either writing our own .sdc file to cater for different design specifications in our future, or to modify the existing attribute values for finer tuning our constraint. So we will go through a brief superficial overview about the .sdc attribute that are used in this experiment, and then we will look at the attributes and the values that are used in the constraint file. This is followed by an overview of the methodology that is used in this experiment. As shown, this methodology will be break down into 4 steps, and by the end we will verify the time slack for the clock that is defined in our SDC file. The whole process will be available in our last part of this experiment video. In general, this synthesized code after following this methodology, that is, after satisfying the constraint and synthesized functional verification, will go to the place and routing process. But here we will hold this particular place and routing flow till our last experiment. Now, focusing back to our synthesis of combo logics, we will move to our first objective, which is the understanding of basics of RTL coding. In digital circuit design, RTL or register transfer level is a design abstraction which models asynchronous digital circuits in terms of the flow of digital signals, that is the data signal, between the registers. Okay, and the logical operations are performed on those signals. A synchronous circuit consists of two kinds of elements. One is the registers, which is a sequential logic. The other is the combinational logic. Registers, usually implemented as D flip-flops, synchronizes the circuit operation to the edges of the clock signal. Combo logics performs all logical operations in the circuit, and it typically consists of logical gates. When designing digital integrated circuits with hardware description language or HDL, the designs are usually engineered at a higher level of abstraction than transistor level or logic gate levels. In HDLs, the designer declares the register and describe the combinational logic by using constructs such as if then else and arithmetic operations like plus, minus, divisions and other stuffs. This level is called register transfer level, and the term refers to the fact that RTL focuses on describing the flow of signal between registers. Now we will look into an RTL example code. The example code is written in Verilog, where the always at positive edge creates registers and the assignment statement performs addition operation using adders, which is basically combo logic. The same is reflected on this figure that is shown on the right. So that's with this short introduction about RTL design and coding, we will move to our second objective, which is the most familiar flow by now. As shown, the synthesizer that we use is RC or RTL compiler from Cadence. This tool requires three major inputs. The first, our RTL code that is written in HTL. The second is the standard library containing all four cells, namely D flip-flop, inverter, NOR and NAND gates, which are the required minimum number of cells that a standard cell library should contain in order it to be used in the synthesis flow. Finally, a constraint file with .sdc extension. The output from this synthesizer will be a netlist that replaces the higher level of abstraction that you would have written in your Verilog or HTL code, and there is also a second output file with a .sdc extension, which is written as an auxiliary file for it to be used in the place and routing process.